So we have two distinguished members from the British Interplanetary Society with us today. Patrick Rennie, who is also the Mars Society UK president, and Fabrizio Bernardini, and they are going to talk to us about engineering for Mars. Gentlemen, welcome. Yes.
Okay, thank you. Good evening, good afternoon, good morning to everybody. Depends when you are on this planet. Let's talk about the other planet first. So despite the title, this presentation is about water ice on Mars, again, you can say. But in particular, we will explore why, in our opinion, this is going to affect all future projects or plans to explore this planet, and how it will affect it in ways that we do not think have been well considered so far. So as Susan said, we are from the British Interplanetary Society. We also do other things in our life, of course. And I say that working around Mars is pretty exciting to be attending this conference for the first time. So thanks for the invitation. And in the last decade, you saw a presentation yesterday, studies about the presence of water ice at mid-latitudes provided quantity estimates that are completely different from the common knowledge that has driven Mars exploration so far. Compared with the previous knowledge, the new estimates are so high that may have failed to register as real in many contexts. In fact, we see that most studies of habitats and also the scope of Earth analogs project of experiences, they still fail to consider this aspect. Consider this image, for instance. This is from a preliminary study, and I keep using since a few years already, which was limited to the amount of water ice in the glaciers discovered at that time in 2014. That study set the estimate to be at least 400,000 cubic kilometers of water ice. And we are talking about nearly pure water ice, because we know that for sure. In other words, we think that the availability and accessibility of so much water ice actually force a paradigm shift for what regards the engineering of Mars. And take note that this image only took care of the glaciers, not the ground ice, the subsurface ice layers, and so on. We will see them later. And in the recent year, more detailed studies have concentrated on mapping this critical resource, and the results are more extensive, taking into consideration also ground ice and underground ice layers. So the SWIM study, which has been described yesterday by Dr. Podzik, my colleague actually, if you think about it, it is the very first full global mapping of a resource on another celestial body, which is critical to humans. This is a very first for humankind. An incredible result, which is also driven in good part by Charad, the Italian radar on Mass Reconnaissance Orbit. We should guide all future projects, as it is now guiding the selection of human landing sites. So the point we would like to make this evening for us is that the presence of large quantities of water ice produces major simplifying assumption for every activity, every design, every project that will be conducted on Mars. And it also induces new needs that have to be considered in Mars project, technological needs actually. So all this translates in a different way of solving many problems. And it is also going to drive the way engineering is applied to Mars projects. Let's discuss why. But before that, consider a couple of facts. I put here just some notes, things to remember about how difficult is working on Mars. And consider also the pure ice in the glaciers is at about minus 90 degrees. At minus 80 degrees, the ice is going to be as hard as rock. This is something that must be considered. Note also that without engineering, there is not going to be a beautiful habitat or anything else we want to do on Mars. Engineering comes first, and we have to take care of that. So, what is driving this paradigm shift is the incredible or the huge quantity of accessible water ice. Accessible is the key part. And this ice has to be extracted. It has to be stored. It has to be processed. And the products of the processing itself, it could be fuel, it could be oxygen, it could be air, it could be propellants, whatever. It has to be stored also. So the storage of these products is also critical for any human activity on Mars, because without these products, you cannot do anything. You cannot properly design anything else. All this, which is the extraction, the storage, and the processing of the materials, requires also energy, and requires machinery, and requires structures. For the energy, you can see yesterday's presentation about nuclear fission generator. It was a fantastic presentation, and it's really enlightening, and it was right on the spot. It could have been part of this presentation, actually. Machinery, structures, and energy all need engineering with appropriate methods and standards designed for Mars. In particular, we have to highlight also the importance of maintenance. And for maintenance itself, we need a specific engineering approach since the very early stage of any Martian project. So what we have to do is, in this case, to engineer maintenance into the designs, because on Mars, you cannot rely on NASA-like or ESA-like spacecraft components. Sophisticated technologies that the one you use in spacecrafts can be killers if you can't fix them. And you cannot count forever on space parts. And of course, the nearest hardware store is pretty unreachable. Therefore, we think that the science shall include the possibility of what we call creative human maintenance. And to enable this, a good starting point is the standardization. Standardization is something that has to be enforced for tools, material, processes, interfaces, and components. It's also important to avoid too many different things, and because we want to use as much as possible similar in part on components in different projects. Otherwise, it's just a confusion of things and useless parts. And please, let's avoid to have both imperial and metric on Mars. I give you a suggestion. Metric could be better, but I'm not going to enforce this. Let's take as an example the tunnel boring machines. The tunnel boring machines are, on Earth can be small, medium, and large, very large sometimes, a huge machine. Sometimes they are built only for a single use. We are not proposing the tunnel boring machine as a solution. We are not talking about solutions here. What we are using the tunnel boring machine as an example of engineering. However, it could actually be a very good solution for Mars, because we will see that later. But anyway, the TBM has very nice characteristics. It's a very simple conceptually. It has an electrical motor, replaceable. It has a replaceable actuator. You see the blue parts here. And you also have the couplers that can be replaced. Every component can also be swapped with other systems. For example, the motor can be used also for another system, but also the motor can be repaired on Mars if it is designed according to guidelines that enforce simplification and commonalization of parts. So why the TBM is very useful actually? Because this is an example of good engineering in the sense that this, let's call it a tool, can also solve other problems. It is going to be used for the main thing, that is getting to the ice. But it also provides help with other problems like the extraction of the ice, because grinding it, remember that it's as hard as a rock, it can save a lot in melting energy, and also can provide in the hole that it produces in the end, it can provide shelter for early habitats. The first holes we will drive in the glaciers using these can be useful with inflatable modules, the one that also Thales Alenia Space showed this morning, and they can be easily used in this condition. We provide also radiation shields and everything. So a solution, if with a single machine, you take care of at least 3 different main problems. Another critical aspect to consider is uncertainties. Engineering shall always take care of uncertainties, even of the unforeseen ones. So applying typical spacecraft redundancy in this case is going to be impractical. And in general, redundancy at system level, so that is replace the entire system, it's not really a good idea, because it should actually target a differentiation instead of duplication. There is an example here about having as a primary power source a nuclear fission reactor, and the main alternative could be solar arrays. And also a backup could be found, because if you store the propellants you can, in case of emergency, use the propellants to produce energy again. So this is a good way of thinking, because you don't want system level issues to create a big problem to the economy. So the redundancy should concentrate on parts and function that should take advantage of commonality among systems, not only for parts and components, but also sharing the functionalities when possible. Therefore, it is, for example, it is important to think in terms of redundancy of the design more than that of the element. And this requires, of course, an engineering of the redundancy to be able to coordinate the design and systems. This and other concepts are going in the end to establish what we call a technological ecosystems in which there is an overall interaction of all the systems, part, component, and tools. So all things can be integrated together, they work together to achieve the project we want to do. Together with standardization, this integrated approach to redundancy also means that the left hand has to know what the right hand does. And there is a simple message. The previous speaker just said that to avoid conflicts in the space community, the same thing. Systems cannot be designed each in their own intellectual vacuum. We have to work together. Who design a system should work together, people doing other systems. Ideally, there should be a guideline, there should be a controlling, not really an authority, but there should be something about a global system engineering method that applies to Mars. Getting back to contingencies, having to deal with contingencies or unforeseen situation and problem is going to be the real challenge for engineering on Mars. So it will be necessary not only to fix, but also to rebuild parts and create tools. In this, the planet's ability to recycle parts, components, and materials will be a critical advantage. So we are talking about a recycling technology at all levels. So you have to build for recycling, like we do today. For example, the packaging of certain products are built for recycling. No, we have to do the same things for the design that goes to Mars, because if something breaks, you cannot use it anymore. You can split it into smaller parts and use it for other things, for example. SpaceX already indicated this, because the first Starship to land on Mars are going to stay on Mars, and they will be used for spare parts and materials and steel especially. Uncertainties may require developing a new solution, and a good dose of the so-called maker attitude will be useful, as well as a good equipped workshop, because you need a workshop to do making, as everybody knows. And so in the end, also design criteria will have to be defined, so to permit that elements are adaptable to multiple uses, or also design which are based on modularity, which is contrary. Today we do a very tight integration of every system, but no, we have to try to do modular components that participate in multiple design. And of course we need good interfaces, because good interfaces anyway are the basis for system engineering in any context. Let's now consider a little bit the location factor. And different landing sites with multiple sources of water ice of different kinds, just to reduce the risk of the first landings, are under evaluation. But one of the 3-4 major ones is the area called Deuternilus Mense. This is the Latin pronunciation. And is one of the best places, in our opinion, to implement a large-scale approach to colonize Mars. We are taking large scale here, and there are good reasons to that. You will see that in the next slide. Consider the picture on the right. This comes from Mars Express high-resolution stereo camera. And this is an overview of a corner of the Deuternilus Mense. And it's a very good picture, but maybe you don't see really everything. But all these features you see around this kind of mountains, these are actually called the mesas by my geologist friends. And all this area, all these things, and it is water ice. Look at this map from the top. This is, of course, it's just a rendering of the altimetry data. This is just a small portion of this area, and this is a square which is 150 kilometers per side. And this area is probably large, as large as least 4 or 5 times this, even more. If you look at these mesas from the top, you see that they are very flat. This is why they are called mesas. And you see that they are surrounded by this area, I don't know how to say that in English, but basically there is something around them. Well, this is something around them. It's what we call the debris-covered glaciers. These are the famous glaciers on Mars that have discovered by radar. And we are talking, consider this is 150 kilometers, you understand the size of these glaciers. These glaciers, they can reach at the ice point something like an average of 400 meters, and they are extend for many kilometers. The amount of water ice in this area is unthinkable. It's really unthinkable. And the idea of having also these mountains, they provide additional shielding for the habitats, but also they provide also landscape. Some places on Mars are really flat and boring. Look at the typical landing sites that are usually very flat and boring, but for good safety reasons. But this area is also nice to see. I have one of our geologists in our team say this is a good place for hiking. And but also they offer the possibility of having probably caves or fractures in the rock, in the sides of the mountains that can permit the creation of cliff-dwelling habitats like the one you see here on the left from Mesa Verde in Colorado. So this area, for example, just imagine if you have an opening like this and we can close it and we can pressurize it, and then inside this area, using local materials, and using all the water ice we want, all the water we want, we can build housing using local material. We don't have any fancy or exotic material imported from Earth to build the houses for a colony. This is me thinking big, but it also means building bricks on Mars, for example. This is the reason why engineering should start since the very beginning with a large-scale approach, because this area is huge and it permits a lot of things. Another consideration about this is that you cannot do this immediately from the start. So there is going to be an evolutionary approach. So we just define 3 stages. We call them the campsite. The first one, where you land, you start putting up some modules. Maybe what is the first thing you do? You start excavating ice and producing water and propellant. This is important because you want to come back, okay? Then you start developing better the area and it becomes a settlement. And this settlement is going again to increase what the extraction of water ice and the production of propellants again, and also setting up energy. And then you keep scaling up things, working in the same area and keep doing the same thing. These 3 stages are nothing new for this community, of course, but consider the emphasis on water ice extraction and propellant production. So we can start small, but this is not so small. You will see that in the next slide. Then we have to start immediately extraction, processing, and storage immediately from the very start. And also considering new resources should be also considered. We have to set up agronomy and things. All these things, the common factor for everything will be the technology used in Mars, and therefore their engineering. Machinery, structures, tools shall evolve, and they will be able to evolve only if appropriate methods are followed. So we are not proposing an approach here. What we are proposing is that there are guidelines needed to make it happen. And from now on, it's on Patrick.
Thank you, Fabrizio. So hopefully we've already convinced you that there is a functionally limitless abundance of water ice. But so what? Okay, well, let's talk about scale for a second then. Consider this as an example of scale where, okay, we're going to have to make quite a few assumptions to start with. So take a starship, launch your cargo ship in an appropriate launch window. We're aware of the synodic period of Earth and Mars, so say every 2.2 years or so. So you launch your cargo ship, and let's get a bit sporty. Let's assume we can arrive on the surface of Mars in 150 days, down from the typical Homer transfer of, say, 240. Really, after you've landed, you want to get the ship filled up before humans even opt to leave from the surface of the Earth. Okay, so if you take that synodic period again, and you say we have about, therefore, 630 days to fill Starship up, that means we now have to manufacture, in round numbers, 1,200 tons of propellant. That's the combination, of course, of methane and oxygen, sorry. In really, really round numbers, if you take into account say, pure water ice and a perfect Sabatier reaction and perfect electrolysis of the water to split it into hydrogen and oxygen, ignoring how much energy it takes, we're still talking about over 1,000 tons of pure ice to completely fill the Starship. Now, those major caveats of the really broad assumptions we've just made there also don't take into account how much propellant is actually needed to fill Starship to come home. I can't make any assumptions. I'm not a SpaceX engineer. I don't know what the delta V to come home is, so can't make a guess. But let's say that we fill it up completely. It's that 1,200. That's also ignoring how much ice is needed to be processed for the people that are going to arrive. So it's probably a minimum assumption, and we're now talking in the thousands of tons over the 2-year period or so that the ship will need to be generating the methane and oxygen over. So now, hopefully, we are thinking big, okay? And this is just the first few missions, because this is what's needed from the start. This is to come home again on one ship. So now we're thinking big. So why isn't that compatible with the current engineering paradigm? Well, because at the moment, most of what we carry to Mars or to the moon, wherever we choose to go, is going to be, in the current paradigm, spare parts for highly complex and niche systems. We are limiting ourselves on the scale of possible missions when we have to bring everything with us. So we shouldn't. The next slide, please. So we've already shown you this diagram. Fabrizio presented it earlier, but let's summarize the main points that we've been trying to get across here. So the first one is abundant water ice enables us to think differently about how we conduct missions to Mars. We should rethink what redundancy means. Just dwell on that word for a second, the word redundancy. We can't sustainably bring a huge proportion of spare parts when we're talking on the large scales of missions. It's completely impractical. So we need to design everything from the outset to be standardized. As Fabrizio said, interfaces need to be the same. We don't want to be on Mars and figure out that the valve on the water tank can't be replaced because the other systems don't match it. We can't afford that. Tools will need to be the same. I'm sure I'm not the only one. I'm sure there are piles of us with piles of different screwdrivers and spanners sat in the garage just for that one job that you need it for. Parts need to at least be modular and or be capable instead of being rigged up for another job. A different type of redundancy, as Fabrizio said, a differentiation redundancy, where one part could do multiple jobs. And so in the whole ecosystem of parts, you can cover your redundancy without necessarily having spares of everything all the time. Everything needs to be fixable. If we absolutely can't fix something, then at least we should be able to strip it down for those parts and give them to the other systems. And all of this needs to be thought about from the very beginning. Next slide, please. So we have presented some engineering ideas, all founded on the proposition of the vast amounts of accessible water ice, in case that point hasn't been drilled home enough. So where can we go from here? We propose an integrated effort to guide the principles of how to engineer for the human exploration and settlement of Mars. We're not proposing the answers, possible missions, habitat designs, or anything like that, but instead the framework by which you would architect those things. This is the systems engineering of Mars. The next step we propose is to take this forward as a technical project by the British Interplanetary Society, just like some historic programs that have come before. However, next slide, please. We can't do this alone. This is a call to action for interested parties to reach out to us. Our details will be on the next slide, so that we can carry this paradigm shift into the next phase. And just to be clear, what you can see in this picture now, these mountains, they are completely surrounded by debris-covered glaciers. The peaks in this image are about 2 kilometers tall, which means the surrounding glacier is many kilometers across and perhaps hundreds of meters deep.
You have 5 minutes left, Patrick.
Thank you. Just to dwell on that for a second, we're all blown away by the sheer size of Starship, right? It's enormous. But when you next gaze upon its magnificent height, realize that it is absolutely dwarfed by this glacier. You would struggle to make it out in this picture. So let us take advantage of this staggering resource and exploit it for the good of humans to Mars. Thank you.
Thanks to all for listening to us. We are open to questions.
Absolutely.
All right. Thank you very much, Patrick and Fabrizio. My name is Lara, and I'm going to ask a couple of questions on behalf of the audience. So
Please.
the first question is, for orbiting structures and associated construction, has there been consideration for using space junk for material?
Okay. Do you want to take this one, Fabrizio, or shall I?
Yes, because this is a topic that is really dear to my heart, because I actually wanted to propose it somewhere. I think we are throwing away too much stuff. I think that this is a personal thinking, of course, maybe Patrick does not share this, but I think that instead of burning up stuff into the atmosphere, it's all this precious technology, and even just the aluminum and the other stuff that we bring to the space station and other places, we should actually send them to a higher orbit and do some kind of a graveyard of this hardware. And maybe one day we will have a low propulsion system like a ion engine or something that slowly brings these things in the vicinity of Mars that could be used for the future. That would be a great, yes, that would be a great project. I like this because I am a person that I don't like to throw away things. So my house is a little bit packed full, as you can imagine. But yes, I think this could be something we have to think about that.
Yeah, to add to that, I don't disagree with your point there, Fabrizio. We are quite wasteful in low Earth orbit. I would add that it's significantly easier to get to low Earth orbit than it is to get to Mars, and the utility of space junk might be really difficult to recycle. So the idea about chucking it somewhere for the future generations to solve, I don't disagree with that. For the immediate term, I think it would be really hard to recycle space junk. I'm all for getting rid of it, but I don't know how one would recycle it at the present time.
I can have ideas. The next one.
Thank you. So the next question is, for Mars infrastructure and maintainability issues, would additive manufacturing, 3D printing be beneficial?
That's for you, Patrick.
Okay. Well, I've actually seen alternative presentations from the likes of European Space Agency, a colleague, shall we say, called Dr. Advanit Makaya, who advocates for 3D printing the Martian regolith on the surface. In terms of maintainability, 3D printers are quite attractive. There will be some engineering constraints on the operation of a 3D printing machine. I would not be certain how to additively manufacture using metals on the surface of Mars. If you were to think about the typical plastic hobbyist machines that we might have at home, they're really good for recycling and maintainability and reuse, because ultimately, if you have a material that you can melt down and reuse, then it is vastly recyclable in any which way. I know from personal experience with 3D printing that recycling the filament is quite challenging to do, and it lowers the structural integrity of the filament when you recycle it. But I think the concept, the philosophy, is a good one. I hope that answers the question.
Gentlemen, we are out of time, but we thank you very, very much for being with us today. Brilliant work, very exciting. Thanks for being with us, gentlemen.
Thank you.
Susan.